Hello and namaste everyone. Welcome to lecture 12 of this NPTEL course on stochastic approximation. In the previous class, we looked at the definition of Martingale sequences, Martingale difference sequences, and also at some examples of Martingale sequences. In this class, we will go a step beyond and look at some nice properties of Martingale sequences and then make some initial or prove some initial results that will help us understand the conditions under which a Martingale sequence can converge. Alright. So, in particular in this class we will look at the construction of new Martingale sequences from existing Martingale sequences, and also we will focus on what is called as the Doob's upcrossing lemma. For this for this week's discussion, I will be mostly relying on this textbook called as Probability with Martingales by David Williams, right. And whenever I refer to a particular result, I will actually refer to it from this textbook, right. So, before we sort of look at this construction of new martingales, we need to understand this special type of process which is called as the previsible process, right. So, a stochastic process Cn where n is greater than equal to 1. So, this stochastic process is said to be previsible with respect to a filtration Fn if the following property holds, that is Cn is measurable with respect to Fn minus 1 for n greater than equal to 1. So, recall that when we spoke about adapted process, we required that this nth random variable be measurable with respect to Fn. Now, in a previsible stochastic process, we have that Cn is actually measurable with respect to Fn minus 1, right. So, now we will use this such a previsible sequence to construct a martingale. In fact, in this example we will see how to construct a super martingale, and because a martingale is a special case of a super martingale, the result will also apply for martingales, right. So, in this result we require that Cn be a bounded non-negative previsible process, right, and furthermore we require that this absolute value of Cn of omega be less than equal to k. So, we require this bound to hold for every n and every little omega in capital omega, okay. So, furthermore, suppose that xn comma fn sequence is a super martingale. So, again this notation over here means that xn is adapted with respect to fn and is a super martingale, in that on an average this xn sequence actually decreases. Now, let us construct a new sequence using xn and cn using the following rule. So, the new sequence will be denoted by yn and y0 equals 0, and for every n bigger than equal to 1, yn equals the sum that is given over here. So, you can see that here we look at the sum of k going from 1 to n, and we have ck times this difference xk minus 1, right. So, if you expand this, we would have this equals c1 times x1 minus x0 plus c2 times x2 minus x1 and all the way up till Cn times xn minus xn minus 1. And the claim is that this new sequence yn that is generated in the following way is a super martingale if xn is a super martingale. Alternatively, if xn is a martingale, then this also the yn sequence will also be a martingale, okay. So, let us go over the proof of this result. From the definition of yn, it is easy to see that yn equals yn minus 1 plus Cn times xn minus xn minus 1, that is we have just separated out the last term in the sum, right. So, now if you look at the conditional expectation of this additional term, right, we can say that the conditional expectation of this expression given Fn, where Fn is the given filtration, that is the filtration with respect to which your xn sequence is a super martingale, right. So, if you take the conditional expectation of this expression with respect to Fn, we can say that this conditional expectation equals this, and this holds because Cn is previsible. Okay, so I think I made a mistake here. This should be Fn minus 1 here. Sorry about that. Okay, so because your Cn is previsible, that implies Cn is measurable with respect to Fn minus 1, and hence we can pull it outside this conditional expectation and write it as Cn times the conditional expectation of the difference between xn and xn minus 1. Right. Now, by invoking the linearity of conditional expectation, we can write this as the conditional expectation of xn given Fn minus 1 and the conditional expectation of xn minus 1 given Fn minus 1. Now, since xn is a Martingale sequence, it is adapted. In particular, your xn minus 1 is measurable with respect to Fn minus 1, and hence this conditional expectation, that is the conditional expectation of xn minus 1 given Fn minus 1, becomes xn minus 1 itself, right, and hence we would have this expression. Now, because your xn is a super martingale, this expression is upper bounded by xn minus 1, and if you take the difference between xn minus 1 and xn minus 1, we would end up with 0, and this inequality is the same as this inequality because this Cn is a non-negative process, right. So, this inequality holds because xn is a super martingale and Cn is greater than equal to 0, right. Now, if you combine these two equations, one can conclude that the conditional expectation of yn given Fn minus 1 is less than equal to yn minus 1. So, let me just officially write that down. The conditional expectation of yn given Fn minus 1 is almost surely less than yn minus 1, and since this relation holds for all n bigger than equal to 1, one can conclude that your yn is actually a super martingale as desired. Okay. All right. So, this was the the first result that we wanted to discuss, and in particular you can see that by a given, I mean using a given martingale or a super martingale and a previsible process, we can actually construct a new martingale or a corresponding super martingale, right. So, with that result in place, right, we can now talk about the super martingale convergence result, right, and in particular we need to first understand this concept called as an upcrossing, right. This will be needed to make sense of the super martingale convergence. Okay. So, what is an upcrossing? So, for an upcrossing we first need a stochastic process. To define upcrossings, we do not need martingale sequences or a stochastic process that has some special property. We can talk about upcrossing with respect to any stochastic process. So, let xn be some arbitrary stochastic process and let a and b be two real numbers with the property that a is less than equal to b, right. And now we will want we want to talk about the number of upcrossings of this interval AB. So, the closed interval AB made by your xn process. Okay. So, let me again repeat this. We have been given this stochastic process xn, right, and we want to look at the number of upcrossings made by this process xn of the interval AB, right, in the time window 0 to n, and we will denote the number of upcrossings by un a comma b, right. So, because this xn is a stochastic process, it is not difficult to see that this un of ab will actually be a random number, right. So, now let us look at multiple interpretations of what this UNAB is. In particular, we will try to get a good understanding of what this UNAB is, and I also have a picture later on to illustrate what this UNAB is, right. So, let us look at an algebraic description first. For every sample point little omega in your sample space capital omega, UNAB of omega, okay, this is the largest k such that the following two properties hold. The first property is that we should have S1, T1, S2, T2 all the way up till Sk, Tk satisfying the following inequality, that is your S1 should be greater than equal to 0, it should be strictly be less than T1, T1 should be strictly less than S2, S2 should be strictly be less than T2, and all the way up till Sk being strictly less than Tk and Tk being less than equal to n, where this n is the end point of your interval, right. So UNAB is the largest k such that this sequence of inequalities hold. Furthermore, at every I your x Si of omega, that is Si is some integer, right. So x Si is the value of this sequence at time Si. We require that this x Si be strictly less than a and xti of omega be strictly bigger than b, and we require this to hold for every I between 1 to k. So in words, the idea is that at time Si your process should be below a, and at time instance Ti the process should be above b, right. And by upcrossing we mean that you start from below a and go all the way above b. So this starting from below a and crossing b is what is referred to as an upcrossing, right. So now we will pictorially try to understand what is an upcrossing, right. So let us look at a pictorial description. So here is the picture that is given. So on the x axis we have time and the y axis we have values, and you see these two horizontal lines where I have marked a and b, right. So we only require that a be less than equal to b, and I have identified some arbitrary places for this a and b, right. And you see these dots with circles, these are the values of your xn process, right. And you can see that at some places you have this circle which is, I mean, at certain time instances these circles are unshaded, and at certain time instances these circles are shaded, and I will tell you when it is shaded and when it is not shaded. Okay, at a very high level the shading denotes an upcrossing. So you can see that from here to here, right, you have one upcrossing, right, and at this point you started an upcrossing but it did not finish, right. So the upcrossing started and it did not finish, right. So this example over here is to illustrate that when I mean an upcrossing, or when I say upcrossing, I do not mean that something has to monotonically increase. We only require that it starts below a and then goes above b, right. So let us now try to understand this notion of upcrossing, right. So you can see that at this point, right, at this point which is 3 over here, we went below a for the first time, right, we went below a for the first time, right, and at time instance 4 we have sort of shaded this circle. This circle being shaded implies that an upcrossing is in process, right. So we go from here to here, the upcrossing continues, we go from here to here. Now notice that at this point, which is time instance 7 or maybe 6, right, yeah, time instance 6, right, we go above this value of b, right, and as soon as we go above the value of b, the upcrossing ends, and you can see that the next circle is no longer shaded, right. So this is not shaded again because we are not below a. So the upcrossing means you have to start below a and go all the way to b, right, and since we have not gone below a yet, the second upcrossing has not started. So at this point in time you go below a, so again the upcrossing starts, so that is why the next circle is shaded. Now this circle goes below because xn can take a value below also, and this upcrossing has not ended, and hence when you consider n equals 11, the number of upcrossings of AB is actually only 1, which is determined by these 3 values over here. Is this okay? So I hope the pictorial description of an upcrossing is clear. Okay. So now what we will do is we will try to formally denote a process which counts these upcrossings, right, and somehow relate it to your super martingale process. Is this okay? In fact, this result applies to any stochastic process, and we will use this inequality, the one that is given over here, later on for super martingales. Okay, so this result applies for any stochastic process, and this result is denoted as the Doob's upcrossing lemma, one of the fundamental results in martingale theory, and this number over here corresponds to the number in this textbook called as probability with martingales by David Williams. Okay. So what does this lemma say? This lemma says that let un be a, okay, there is a mistake over here, it should say let xn be a stochastic process, okay, and un be the number of upcrossings of the interval AB by time n of this stochastic process xn, right. So this result requires that you have some stochastic process, and UNAB looks at the number of times this process starts below A and goes above B until time n, right, and the claim is that for this stochastic process, if you look at the expected value of upcrossings and multiply it by B minus A, then this expression will be upper bounded by the expected value of xn minus A minus. Okay, so actually I realize that for this result also we require things to be a super martingale. So I take back what I said, this is actually incorrect. We require that your xn be a super martingale. Okay. So let me again state the statement of this result because I made a mistake. So we require that xn be a super martingale and un be the number of upcrossings of this interval AB. Then the claim is that B minus A times expected value of UNAB is less than equal to the expected value of xn minus A minus. Okay, so let me first tell you what does this notation mean. Okay, for any real number, okay, let us say the real number is R, then R minus is the max of minus R comma 0, right. So in other words, if you have if R equals minus 2, then R minus equals 2. On the other hand, if R minus is 3, then if R is 3, right, then R minus equals 0. Is this okay? So in other words, whenever the argument to this superscript minus is negative, then the output is some positive number. On the other hand, if the argument to this superscript minus is positive, then the output is actually 0. Now we extrapolate this definition to random variable itself. So xn minus A, right, is some real number for different little omegas. So you take that number, now either that number can be positive or negative, and depending on whether it is positive or negative, you define this minus superscript minus operation. So that will be another random variable and you can take its expectation. Okay. So this is the claim and we will now prove this claim, right. So towards that, what we will do is we will first define a previsible process, right. So what is this previsible process? The previsible process we will denote by Cn, and the first element in this process will be C1, which is said to be the indicator that x0 is less than A. So notice that C1, because it is of the indicator function, can either take the value plus 1 or 0, and it will take the value plus 1 if x0, that is notice the index is actually 1 less than this index, right. So if x0 is strictly less than A, so C1 will be 1, indicating that your upcrossing has begun at time 0 itself. On the other hand, if x0 is above A, then your upcrossing has not begun, right. And then this Cn is actually defined in a iterative fashion. So Cn either can be 1 if these two conditions simultaneously hold, or it will be 1 if these two conditions simultaneously hold. So let's look at these two conditions. It says that an upcrossing was already going on, that is what Cn minus 1 equals 1 indicates, and the previous value was still below B, right. So because this was 1 and the previous value was still below B, the upcrossing is still going on and hence Cn should be 1. On the other hand, Cn minus 1 equals 0 implies that there was no ongoing upcrossing, and now because your xn minus 1 is strictly less than A, an new upcrossing has begun. Is this okay? So in either of these two scenarios, Cn will take the value 1, right, and one can easily check that because of these two things being complementary events, either this product will be 1 or this product will be 1, and also notice that Cn is a function of only Cn minus 1 and xn minus 1, and consequently your Cn will be measurable with respect to Fn minus 1. In other words, your Cn process will be previsible, okay, right, and it is easy to see that your Cn will actually take the value 1 only during an upcrossing, right. So now if you go back to this pictorial representation that I had, you can see that the reason I had shaded some circles and left some circles unshaded was primarily those time correspond to primarily those time instances where Cn took the value 1. So you can look at the definition of Cn and conclude for yourself that C4 is 1 over here, C5 is 1 over here, C6 is 1 over here, however C7 is 0 and so on and so forth, right, and the value of C4 for instance only depends on what happens at this point. Similarly, the value of C5 only depends on what happens here and so on and so forth. So that sort of illustrates what a previsible process is, right, and now our goal is to prove this inequality. So towards that, what we will do is we will first define this stochastic process yn in the following way. So we will first set y0 equals 0 and yn equals this sum of first n elements as we had done in the previous lemma, right. And because we have defined in this way and your ck's are bounded non-negative random variables and they are also previsible, it is easy to conclude that this sequence yn is a super martingale based on the previous lemma, right. And now we will look at an alternative description of yn, right, which is very interesting. So yn, one can see, is equal to this sum over here. So let me illustrate how you got this sum, right. So here if you notice, each term here is multiplied by ck. So if ck is 0, this whole expression will be 0. On the other hand, if ck is 1, then this expression will be xk minus 1. So if you look at S1, so before S1 your ck term would be 0 because no upcrossing has begun, but as soon as you go to S1, which is the first time you went to below A, then your C value will become 1 and the first term in this sum wherein the C corresponding C value will be 1 would be this expression, that is C S1 plus 1 is 1 and hence we have this expression, right. And until your upcrossing continues, one can see that you would have some expression like this. Is this okay? And one can see that in this dotted sum we actually have a telescopic sum. By telescopic sum meaning the next term in this expression will be S1 plus 2 minus S1 plus 1 and so on, right. And because of this telescopic sum we would be able to cancel off these terms, cancel off these terms and eventually cancel off these terms, and we will only be left with xt1 minus xs1, right. And similarly we will have another telescopic sum for the next upcrossing which will start at S2 and go all the way up till T2, right. So again we have a bunch of dots here indicating that this sequential difference will start at S2 and go all the way up till T2, right, and this will continue until the kth upcrossing, right, and then finally, right, so this is the kth upcrossing, right, and finally we will have some additional terms over here. Okay, so this additional terms correspond to this upcrossing which began but couldn't complete, right, which began but couldn't complete. So this is the last term that we have over here, right. So this term, so recall that on the left hand side you have yn, right. So this yn will equal things related to your k upcrossings, and finally some term which corresponds to the last upcrossing which started but did not complete, right. So again from the telescopic nature we would have xn minus xk plus 1, okay. So this is the plus 1 is over k itself, whereas this plus 1 is over after sk, right. So this is sk plus 1 and this is multiplied by the indicator that your sk plus 1 is less than equal to n. So let us understand why do we need this indicator. So it is possible that the last upcrossing never started, in which case this indicator will be 0. On the other hand, the last upcrossing didn't started but didn't complete, in which case this indicator will be 1 and we will be having this term over here, right. So now as I mentioned over here, because of this telescopic nature, this whole expression will only end up containing xt1 minus xs1, and by our definitions of t1 and s1, right, this expression will be above b and this expression will be strictly less than a, and hence this term will be greater than b minus a, right. And one can see that every such upcrossing will lead to a term which is greater than equal to b minus a, and hence until this point one can conclude that the expression is b minus a times the number of upcrossings, and then we have this tail part which comes over here, right. So at the end one can conclude that this yn term is greater than equal to the number of upcrossings, okay, I think I missed a term here, this should be b minus a times this, okay, minus this last part, okay. So why is this minus? It basically follows because of this expression, and I leave it as an exercise to show why this expression is less than equal to this part over here, and I will just show you some hints on how you can prove this, okay. So let us say you have a here and let us say this is xk plus 1, okay. Now xk plus 1 should definitely be your sk plus 1 should be strictly less than a, however your xn either can be here, either can be here, or it can be above your line a. So you consider these three different cases, and in either of these cases check whether this expression is greater than equal to minus of xn minus a, okay, with a superscript minus, right. Now we can use the fact that yn is a super martingale to then recall that the conditional expectation of yn given fn minus 1 is almost surely less than yn minus 1, which if you take expectations on both sides implies expected value of yn is less than equal to expected value of yn minus 1, okay. So you can use this iterated expectation property to conclude this. Now your yn is actually bigger than equal to this, and we also know that your y0 is 0, right. So y0 is 0 and your expectations satisfy this property and yn is bigger than equal to this. So if you put all of them together, one can conclude that expected value of yn is less than equal to 0, and hence 0 must be greater than equal to this. So if you move this to this side, one gets the desired result, okay. So this brings us to the end of lecture 12. Let me quickly summarize what we have studied in this class. We looked at a new way to construct a super martingale or a martingale from a given martingale or a super martingale. In particular, we made use of this previsible process and looked at these successive differences multiplied by this previsible process to come up with a new process, and we saw that that process is actually either a super martingale or a martingale depending on whether the xk process itself was a super martingale or a martingale. And then we proved what is called as the Doob's upcrossing lemma. So we will in the next few lectures we will see how this upcrossing lemma can be used to prove the convergence of a super martingale and hence also of a martingale. In particular, in this upcrossing lemma, we were able to relate the number of times a process crosses this interval AB, right, in terms of the value of the process at time n, right. So let me just show you that last expression, right. I think there is a mistake here, sorry, I should have written little n over here. So then for all n bigger than equal to 1, this holds. Okay, so the way to read this process is that the number of upcrossings between 0 and n is upper bounded by the value of the process at time n in terms of this function. So you will see that this result actually plays a very crucial role in discussing convergence of super martingales. With this I would like to stop. See you in the next class. Thank you and namaste.